Okay, yesterday we were talking about sequence networks of the alternator, and we have drawn this diagram, and after that we have applied the Kirchhoff's law. Now, as we know that sequence synchronous machine generates balanced set of three-phase internal voltage and is represented by positive sequence. So it generates inside it a balanced set of three-phase internal voltage, and that's represented by the positive sequence setup. This is a positive sequence set of phasors ABC. Okay, now we apply the KVL to one of the phase, then we can extend the same to the other phases. So I will write down that applying KVL, what we have got, VA is EA minus ZSIA, already I have done it yesterday, minus ZN IN. Similarly, we have to write for VB. VB will be EB minus ZSIB minus ZNIN. And VC will be EC minus ZSIC okay, minus ZNIN. Now, writing this equation in the matrix form, writing the above equations matrix form. So we'll write this in matrix form like this. Okay, so this will be equal to okay, minus, we'll have this impedance matrix. Who is this Adiba? She's our student. हाँ जी बेटा, सना?
No sir, अदीबा नहीं है आई गेस क्लास में कोई.
Who is Uzair 45? Uzair is our student, है ना?
Yes sir.
Adiba कहाँ की student है?
Sir मुझे I don't remember any अदीबा.
Okay. Now this is, we'll write this in the matrix form. You can see ZS plus ZN, and when we'll write this in the matrix form, this will be ZS plus ZN. How I will first explain it here. Now here we can see from here, if we take one of the faces, so we can write down this as ZS plus ZN into IA. Now we'll be multiplying. Okay, let us leave it first. I will explain it later. Just a second. Okay. Now impedances will be ZS plus ZN. How come? Because IN will be equal to what? IA plus IB plus IC. So I'll write this as ZN plus, sorry, ZS plus ZN, because one of them will be common with IA. Then this will become Zn, this will become Zn, this is Zn, this is Zs plus Zn, this is Zn, this is Zn, this is Zn, and this is again Zs plus Zs. Just a second, I will explain this. multiplied by I, A, IB, and IC. There will not be IN now. How come we have got this? You can have a look here. See, we had minus ZS plus ZN. Okay. See, this Zn, IN will be equal to, here we can write IN will be equal to, IN is neutral current, IA plus IB plus IC. So out of this, minus I am taking out, ZS plus Zn, that means IA will come common. Rest with Zn will be IA plus IB plus IC. So I will take common here, and with Zn what we have, we will have two currents left, that is IB plus IC. Okay, so further we can write it minus, this will be ZS IA, then we have Zn IA, then okay, then same thing we have IB plus IC. So what I am going to do here, I am going to take Zn minus ZS IA, then we can write here IN IA plus Zn, sorry, IB plus IC, and we know that this is equal to Zn minus ZS IA plus Zn IN. So that's why instead of this, which was already present, ZS you take common, this, sorry, plus minus you take outside, that is ZS IA plus Zn In. This was originally there. So instead of this, we can write this. So that's what we have written it here. So we can solve this, and this exactly will become the same as the original matrix is. There's no difference in all. Okay. Then further, we also know IA plus IB plus IC is neutral current. If we have unbalanced currents, that will be neutral current. So we can write this equation here as VABC, EABC, and ZABC and IABC. So in short form, we can write, or I will write, name this equation. Equation 1 is here. Okay, equation 1 can be written as, so we can write it, VABC will be equal to EABC minus ZABC and then IABC, where VABC will be phase terminal voltage vector, whereas IABC we will call it, IABC is phase current vector. This is phase voltage vector, simply you can write phase current vector. Okay, now let's transform this equation, equation number 2, we can write it into the symmetrical components. Transforming equation 2 into symmetrical components. Okay, once we transform that, what we have to do, we have to multiply by vector A, sorry, matrix A. So that will be VA 0, 1, 2, and this A, EA 0, 1, 2 minus ZABC will be as usual, IA, that is A, IA 0, 1, 2. Now we know this is in the symmetrical component. So we know what is in the symmetrical component, how we will get it. We have to multiply by the vector A, voltages and currents. Okay, after that, now in order to solve this, we multiplying above equation by A inverse. Multiplying above equation by A inverse. Okay, now we multiply A inverse and A will go inverse, and same matrix will be unit matrix, anything multiply by any matrix will be that matrix. I've already told you. Next, A inverse and A inverse same. We have a voltage at this EMF matrix minus A inverse ZABC multiplied by A. Okay, this is A inverse here, and if you multiply this, this will be A, this one. Rest of all will be the same matrix. Now let's see what we are going to get. Now this above equation, in this case we have to solve this side, right hand side we have to solve, particularly this side up to A inverse ZABN up to IA. This we can leave it for the time being, so we'll see. So this part will be solving A inverse multiplied by ZABC multiplied by A, which will be equal to, okay, which will be equal to what? This is A inverse is 1 by 3 bracket 1 1 1 1 A square 1 A square A, and then ZABC we know that is ZS plus ZN, ZS plus ZN, 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 ZS plus ZN, Zn, and then we have Zn, Zn, Zs plus Zn, and multiplied by A matrix we already have done number of times, that will be 1 1 1 1 A square A 1 A square. So if we'll solve this, we will name it, let's name it this value, we name it Z0 1 2. Let's name it Z0 1 2. So if we'll solve this, you can see one of the row I can show you. This will be 1 by 3, then one of the row, then we can, rest of all you can calculate. See, one row will be multiplied by this column, and this will be Zs plus Zn plus Zn plus Zn. So this will be here. Second will be Zn plus Zs plus Zn plus Zn. Okay. Similarly, we will have Zn plus Zn plus Zs plus Zn. And same entries we will have in the similar way we will have here. Okay, I'm not writing that. You can do that later on. Multiplied by here. What is this matrix? This matrix is 1 1 1 1 A square A 1 A square. Okay. Now solving this row a bit, 1 by 3, first row will come out to be Zs plus 3Zn. Okay, again Zs plus 3Zn, and again here Zs plus 3Zn, and then we have this matrix 1 1 1 A square A 1 A square. Okay, now you can, this 1 by 3 will be here. Okay, now you multiply this row, first row with these columns. This will become first row with this column. So it will become Zs plus 3Zn plus ZS plus 3ZN plus ZS plus 3ZN. So one entry of the first row. Second row will become ZS plus 3ZN, okay, plus A square ZS plus 3ZN plus, I'm writing here only, plus A ZS plus 3ZN. Okay, third entry of this row will be ZS plus 3ZN and plus A ZS plus 3ZN plus A square ZS plus 3ZN. So this will become the complete first row. So second rows you can similarly fill, because I can do it. It will just waste the time. It will take a time which is not required. Okay, so this value we can write 1 by 3 in the first row as ZS will be 3ZS. It will be 9. So dividing by this 3, I will not write this 3 here now. I don't know who wants to join now after so much of time. Farhana. Okay, so this is here ZS plus it will become 3ZN. Fine, because we will divide it by 3, this matrix. So this is 3ZS, that will be ZS, divided by 3 will be ZS. 9ZN divided by 3 will be 3. Second entry. Okay, so this is ZS plus 3ZN. Okay, ZS plus 3ZN plus A square ZS plus A square 3ZN plus AZS plus A 3ZN. Okay, and last entry will be ZS plus 3ZN plus AZS plus A3ZN plus A square ZS plus A square, sorry, 3ZN. So rest entries you can fill. The rest of the entries we can fill. Okay, this is the, now you can see here for this 1 by 3 is still valid. Okay, okay, I'm not writing it. So 1 by 3 is, let me write 3 here and 1 by 3, that will make it clear. Okay, fine. Okay, so here I am writing ZS plus ZN now, 3ZN now. I am dividing it by 1 by 3. You can see here ZS, ZS and ZS. So you can take common 1 plus A square will be 0. So this term will become, I'll make it with red. This term, and this term will become 0. Now this here, we can take 3 common, okay? ZS plus A square ZN plus A ZN. Again, this will become 0. So this term will become 0. This is with Zn. So they will become 0. The whole of this term will become 0. So I can write it here. Similarly, this will also become 0, because this is the same thing, only first we have multiplied by A, then we have multiplied by A square. So this will become 0. And if you solve this complete matrix, this will become 0 and this will become ZS, this will 0, this 0, 0 and ZS. You can solve this matrix and you will get it. There is no problem at all. So Z0, 1, 2, I can write it. Instead of this, I will write Z0, 0, 0 and 0. ZS, I will write Z1, Z0, 0, 0, Z2. So here Z0 is equal to ZS plus 3ZN, whereas Z1 is equal to Z2 is equal to ZS. And we also know that E A012, which we have here. Here we have written that. A, this one. So this we have solved. This was equal to Z naught. Okay. So EA012 can be written as only we have. So that is written as 0 EA. Only positive sequence will have value. Rest will be 0. So here we will write down generated voltage EMF. Sorry. Generated voltage, which we also called sometimes EMF, is balanced. This is the reason why we are writing there. Therefore, there is only positive sequence voltage. There is only positive sequence voltage. So writing this complete matrix again. So in symmetrical form, we can write this VA naught, VA1, VA2. So which equation we are writing? We are writing this equation now. Okay, this equation. Okay, instead of this equation number, I will write here. Okay, 3. But further, we have given this name, so we can write VA naught 1, 2, EA 1012 minus this complete term here we have given name as Z0, Z012, and this is IA012. This is so fourth equation we are writing now. Instead of VA naught, okay, instead of VA naught, this is a separate entity here. So this is the equation. So equation fourth can be written as, can write it here. Equation 4 can be written as, so VA0 1 2, instead of this we'll write VA naught, VA1, and VA2, EA012. EA012 we have already seen that this is only the positive sequence will exist. That's the reason for this one. 0 EA0, because reason is generated voltage is balanced and there is only positive sequence voltage. This voltage does not exist. And for this one, Z012 will be Z naught 0 0 0, Z1 0 0 0, Z2, where Z naught, Z12 they have respective values. We have written it above. And for current it is I naught, I1, and I2. Okay. Moving ahead, if we solve this, so we can write 0 sequence voltage will be equal to minus 0 minus Z naught I naught. So this is minus Z naught I naught. But Z naught is equal to Zs plus 3Zn, that we know already. So, and positive sequence will be equal to voltage source is present. That will be Z1 I1. Okay. So negative sequence will be VA2 0 minus Z2 IA2. So we can write it minus Z2 IA2. Okay, so these are the three voltages. We have positive sequence only will have voltage source. Negative sequence and zero sequence will not have voltage source, and the values will be Z0 IA0, Z2 IA0, where Z0 is equal to Zs plus 3Zn. Okay, moving ahead, let us draw the sequence networks for this one. Okay, so we'll draw the sequence networks here. Okay. Okay. So this is positive, this is negative. EA, this is your impedance, and this is for the positive sequence we are drawing first. This voltage is, this voltage will be VA naught, sorry, VA1. Positive will only have voltage, and this will be your Z1. So this is for which sequence? This is for positive sequence. Okay, so add a page here and let us copy this. Okay, copy and paste it here. So for what will be change in the negative sequence? Change in the negative sequence will be no voltage source. Okay, that will be change only. So there is no voltage source here. Okay, there's no voltage source. No voltage source is there. Okay, this will be VA naught for the first will be the negative sequence Z1, and this is for the negative sequence. Negative sequence. Similarly, we'll copy for the zero sequence because voltage sources are not there. Okay, just copy, paste. We'll make it here for the zero sequence. Only difference is that voltages will be VA naught, Z naught, and this is for zero sequence. So these are the sequence networks for the three. If somebody asks you to draw, this is very simple. So you need to draw this positive, negative, and so positive, sorry, positive is 1, negative will be 0, 2. This is 2 here. Positive is 1, negative is 2, 0 is 0. So this is negative sequence. So now, what is the noteworthy what we have to note here? Number one, what we have to note, generated voltages are of positive sequence that I've already told. Only negative, since generated, reason again I am giving, since generator is designed to supply balanced three-phase voltages. Okay, so generator is designed to supply balanced three-phase voltages. That's the reason. Now let's make some observations. This red. Observations are, number one observation is Three sequences are independent. That means positive, negative, zero sequences. They are three sequences are independent. They are not dependent on each other. Nothing. Okay. Next is the positive network sequence network is same as the one line diagram used in studying balanced three phase currents and voltages. The positive sequence network is same as the single line diagram or one line diagram used in studying balanced three phase currents and voltages. Why it's same? Because there also we have a voltage source. Per phase analysis we do there also. Same we are doing in this case also. Only positive sequence contains a voltage source. So that positive sequence, this contains voltage source. Others do not have voltage source. No voltage source for others. That's full. For negative and zero sequence, we don't have voltage source. Next is very important. Condition is of neutral has no effect in representation of generator both in positive and negative sequence networks. So condition of neutral has got no effect in the representation of generator both positive and negative sequence networks. So if we have to draw positive and negative sequence networks, neutral is not going to have any effect in case of for a generator. If we are drawing positive and negative sequence networks, whether the neutral is there is no neutral, ungrounded neutral, or there is a grounded neutral, or there is a reactance grounded neutral, it does not make any difference. So it does not make any sort of difference while you are drawing the positive and negative sequence networks of the generator. But however, it affects the representation of generator. It affects the representation of generator in zero sequence networks. But zero sequence networks, that is definitely there that whatever the case may be, whether the neutral is ungrounded, it's grounded, or its reactance grounded, then it will definitely have effect on the sequence networks. Now let's see what are the three cases for this one. Number one is if the neutral is unloaded, that means it's not grounded. Unloaded means there is no connection of neutral to the ground. So if the neutral is unloaded or ungrounded, it's one and the same thing. If the neutral is unloaded, then we need to show open circuit while drawing the sequence network. Then we need to show open circuit while drawing sequence network. while drawing this zero sequence network. So if neutral is not grounded, unloaded, that means neutral, there's no connection between neutral point and the ground. So then we have, while we are drawing the network, we need to show that as an open circuit. I will clarify it after it. Now, if neutral is solidly grounded, if the neutral is solidly grounded means you know this. This is neutral, this is solidly grounded. So if the neutral is solidly grounded, what will happen? Then while drawing the zero sequence network, we need to show, I will write here only short form, show short circuit. We need to draw it by, we need to represent it by the short circuit. Third is, if the neutral is reactance grounded. If the neutral is reactance grounded. So now we have a neutral that is reactance grounded. Now, if the neutral is reactance grounded, then what we must do, as we have derived it already, then reactance grounded, we will call it Xn. Here I will draw it Xn. Okay. Then 3Xn, we have derived this equation, 3Xn, 3Xn, this is 3Xn, in words, 3Xn must be added to zero sequence reactance of the generator. Let's say that is XGO, zero sequence reactance XGO. We have to add it to get the zero sequence, to get the zero sequence reactance. So that means if zero sequence reactance is represented by X naught, yeah, Z naught, it's one and the same thing, then it will be XGO plus you have to add 3Xn. It's very important. Here we have already derived it. So in case of zero sequence network, if the neutral is reactance grounded, you have to always remember, then in order to write the zero sequence network, zero sequence reactance, sorry, you have to add to what? You have to add to the zero sequence reactance of the generator. You have to add that. For that, you have to add 3Xn, you have to add in additional. So that means the three cases will be there. If in a generator we have positive and negative sequence reactance, whether the neutral is grounded, solidly grounded, it's unloaded, ungrounded, and reactance grounded, it doesn't make any difference. But if we have a generator and we have to draw the zero sequence network for that, then the connection of the neutral is very important for us. And for unloaded or ungrounded, we have to show open circuit. For grounded, solidly grounded, we have to show short circuit. For neutral grounded, we have to add an additional 3Xn to the zero sequence reactance of the generator. Okay, then we can say that three sequence systems can be solved separately. There is a separate phase current and voltages can then be determined. They can be also determined by using the symmetrical components. Now, next point is, which is very important, is in case of generator, positive sequence reactance is almost equal to negative sequence reactance. So let's say this is a positive sequence reactance is almost equal to, it's approximately equal to negative sequence reactance. This is in case of, we are talking about the generator. In case of generator, positive sequence is almost equal to negative sequence. But strictly, if we speak strictly, that means precisely if we are speaking, strictly speaking, xg2 is slightly less than xg1. That means negative sequence reactance is slightly less than positive sequence reactance. Is slightly less than positive sequence reactance, strictly speaking. But if we take in totality, they are almost approximately same. Zero sequence impedance reactance is less than positive sequence reactance. Is less than xg1. That means xg0 is less than xg1. Okay. So this was another point. Now, from this circuits, I am going to explain something. Now we know that zero sequence currents are having the same magnitude and phase in all the phases of the system. That means whether in all the three phases have same, at any point they have same phase and magnitude. We have seen that like this zero sequence, they have magnitude and phase, they have same. If we're talking about the zero sequence currents. Therefore, zero sequence current will flow. When we talk about the zero sequence current, then when they have same phase and magnitude, then zero sequence currents will flow only when they will be having the only if the return path exists. So zero sequence current will flow only if the return path exists for them, if the return path will exist. It's very important, through which we can complete the circuit. The reference of zero sequence voltage is potential of ground. So when we will talk about the reference, zero sequence voltage is ground. Potential of what? We will talk it about. It's a potential of ground. That means it's a ground. I will again repeat. Zero sequence networks at any point of time will always have magnitudes and phases same. So when they have to flow in a closed path. That means they should have a return path in a complete circuit. And the reference of zero sequence voltage will be treated as the ground. That will be at a potential of ground. Now, in if the circuit is star connected with no connection from the neutral, let's talk here with the diagram. Now you can see. Now this is the first case number one. I'll be writing it here, and then this is the network we are drawing. This is the case number two. We have talked about the zero sequence networks, how to draw. We have talked about this. Case number three, and delta is your case number four. Okay. Now, case number one is if we have a star connection, then there is no connection of the neutral with the ground. You can see here, there is no neutral connected here. It's left open. So when it is left open, so neutral is not grounded, in other words, or there is no neutral connected to another ground, just you can see that neutral is not grounded in first case. Now we are going to draw the zero sequence network of the same. Then in this circuit, we can see the sum of the currents IN. Here we can say sum of the currents, neutral currents, IA, it will be IB plus IC. So neutral current will be 0. So this is IA plus IB plus IC will be 0. In other words, IN will be equal to 0. So since the currents whose sum is 0, so in that case, the no zero sequence component will be there. There will be no zero sequence component because sum of the currents is 0 in that case. But the impedance to zero sequence currents is infinite. So if you have anywhere you can see if V is equivalent to ZI, simple Ohm's law in AC way I'm writing, then if I have current equal to I is equivalent to V by Z. this value of current is equal to 0. So this can only become 0. This value will only become 0 when this value on the right hand side will be infinite. So impedance here will be, so impedance to 0 seconds current is infinite, that is beyond the neutral point. So how we indicate that in the network when the neutral is infinite? Neutral is sorry, impedance is infinite, impedance to 0 seconds current is infinite. So how we represent that in the circuit? We represent that by the open circuit, because current does not exist, current does not flow. So this is a reference we were talking about, or this reference is at a ground potential, and uh, this is a impedance, this is a neutral point, and this is the impedance from one of the phases you can take, because per phase basis we are drawing the sequence networks. So this is the neutral point, and this is your impedance of one of the phases. So in between them there is no connection. Why? Because current has no path, current is not flowing, value of the current is 0. At the same time, the infinite, we have impedance as an infinite. When the impedance is infinite, so no current will flow through. So we will represent the first case where the neutral is ungrounded or unloaded. We will represent it by a reference bus and impedance Z of one of the phase connected to from this one side is a neutral point. So in between the reference and this one of the phase will not be, there will be no connection, that will be left open. Because of the reason, the current flowing will be 0. When the current flowing in the neutral at the neutral point will be 0, then impedance will be infinite. Impedance to the, therefore 0 seconds impedance will be infinite. So that's left open circuits. Case number 2. Case number 2 is if the neutral of the star connected circuit is grounded through 0. Now we have grounded through, but value of this impedance is, you can say, let us say this value of impedance is, this value of impedance is 0, because it's a short circuit here. You can see it is grounded, solidly grounded, but impedance value is not there. So when in any case the value of this impedance is 0, so what will happen when this value is 0? So obviously your voltage will become 0. You can see here, no impedance is flowing there. This is a complete short circuit. A wire is there and that's grounded. So when the value of this impedance is 0, that means your voltage will become 0. When your voltage will become 0, that in electrical engineering represented by the short circuit. So between one of the phases of the star connected, because we are drawing the sequence networks on per phase basis. So this is your Z here, Z, and between reference, that's a ground potential between reference and one of the phases, uh, from reference to the neutral point there will be a solid short circuit, that will be connected by a wire. So I will repeat it. If the neutral of star connected circuit is grounded through 0 impedance, a 0 impedance connection is inserted. 0 impedance connection means the value of the impedance is 0. It's a solid wire only. Connection is inserted to connect the neutral point, and the reference bus of 0 sequence networks, it is shown here. So we can represent this 0 sequence network in that case by a connection between one of the phases, that is from the neutral point to the reference, as a short circuit, because of the reason obviously here. Now third case is if the impedance Zn is inserted between the neutral point, this is your neutral point N, and the ground of a star connected circuit. And impedance, now we have derived it last, because why? We know that In is equal to Ia plus Ib plus Ic, and we got this sequence network, this was equal to 3 Ia naught. So it will be 3 times the zero. We are talking about the 0 sequence. So neutral will be 3 times the 0 sequence current. When it will be 3 times the 0 sequence current, so voltage will become impedance into the current. So that will be, if we are talking about the voltage, that will be impedance Zn into this current. So then what we do, this Cn has to be, the Cn will be the total impedance, because current will be Ia not flowing. So 3 Zn has to be, must be placed from the neutral to, so Although the connection is there between ground and the neutral, you can see neutral point and ground connection is there, and this impedance is there between this, one of the phase impedance is Z, but between this reference point, that is at the ground potential, and the neutral point, 3 Z has to be added, because the value of the current, that is value of the current in the neutral in this case will be 3 times the zero sequence component of the current. So that's why 3 times Zn has been inserted between the reference bus and the neutral point. So lost is a delta connection. Now delta connection, since it cannot provide return path, that we know, so it offers what? Offers infinite impedance. So it will offer like this infinite impedance to the zero sequence line currents. The zero sequence network is open. You can see the zero sequence networks will be, because it will offer infinite impedance, is open at the delta connected circuit. So zero sequence currents may circulate, and they may circulate inside the delta, since the delta is a closed series circuit for circulating single phase circuit. So inside the delta they can circulate, but otherwise here it will be open circuit because of the infinite impedance. So this was the very important concept. Is it clear, or beta Sana?
Yes, sir. Clear.
Is there any doubt?
No, sir.
Very important things what I have discussed today. Rutba, roll number 5.
Yes, sir.
Is it clear or not?
Yes, sir.
Any points? Any questions?
Yes, sir.
Anybody has a question? So this was something about, we're talking about the different types of connections which we are having. Now after that, I will give you one small topic for the homework, that is sequence network of unload. It is same what we have discussed, but you can draw the networks for that one. So this topic is for your homework. I will try to study it. Otherwise, this is simple topic: sequence network of unloaded generator. Unloaded means IA, IB, IC is 0. Load is not there. Okay. Okay, that's all. That's all for the today. So next time we will start with the faults, unsymmetrical faults, that is line to ground, double line analysis of those faults, and numericals on those. So we'll be continuing next time. Beta Sana, you can send me the log. I will just stop the recording.
Yes, sir. I will send.